Okay, had some issues there with the first stream. I'm not sure what was up with that, but I think we're good to go now. Sorry for the delay. I know you guys are so excited to get back into chapter 7, confidence intervals. Hopefully you've had some time to look at confidence intervals that we've been talking about already, confidence intervals for the mean. And today we're going to look at confidence intervals for standard deviation, really just for variance, and then take the square root to get standard deviation. And then we'll go into hypothesis testing after that. So if there are no questions, we'll get started. So we'll wait a second for everybody to get here. Let's see if there are any questions over in the chat first to get started. I know we talked about a lot last time. We had we had confidence intervals for the mean, large sample, small sample. When do we use a Z table? When do we use a T table? Stuff like that. So pretty important to know the difference. When do you use a T table? When do you use a Z table, etc. Today we're going to be talking about confidence intervals for variance and standard deviation. And then we'll get into a little bit of hypothesis testing. So let's make sure everybody's here. We'll get started. The test statistic, or the variable right here, this thing varies from sample to sample, so it's a random variable. So this is a random variable, very much like x bar is a random variable. This thing, n minus 1 times s squared over sigma squared, is a random variable. All right, it varies from sample to sample. We don't know what it's going to be beforehand until we calculate it. And it's a random variable that has a chi-squared distribution. We mentioned that distribution back in chapter 4 very briefly. We mentioned it was a special case of these more complicated distributions, but chi-squared distribution is a non-symmetric distribution for the most part. Like, as the degrees of freedom get large, it becomes more and more symmetric. You can kind of see that here in the graphs. But if your degrees of freedom are very small, it's very skew right? It's very non-symmetric. So this, the chi-square distribution right here, depends on, first, your degrees of freedom. The degrees of freedom determine what the shape of the chi-square distribution is going to be. Is it going to be tall and very skew right, or is it going to be kind of wide and short, not so much skewed? Well, that depends on the degrees of freedom. And the degrees of freedom is based on the sample size minus 1. Very similar to what we had last time for degrees of freedom. This is going to be sample size minus 1 to get our degrees of freedom. So sample size minus 1. So what we are going to take from this chi-square distribution is these critical values right here. Chi-squared sub alpha comma nu, or comma v. If you just want to call it v, that's fine. So alpha is the area to the right of the critical value, and v, or nu, is the degrees of freedom that you're considering. So if we wanted to look at chi-squared sub 0.01, so 0.01 comma whatever degrees of freedom, you have 0.01 right here. Well, if you looked at chi-squared sub 0.99 v, that means you have 0.99 over here. So 0.99 to the right. Okay. Now, these two values, these two critical values, are not symmetric. You know, like whenever we had the normal distribution, 1.96 had 0.025 probability to the right, and negative 1.96 would have 0.025 probability to the left. Well, for chi-square, it's not symmetric. This 0.99 critical value is not going to be the negative of the 0.01 critical value. So these things are not symmetric. So that's important to keep in mind. If we need both of them, we have to look them up separately in the table. So we will always need these two critical values. When we look them up in the table, we have to always look up two critical values, since this distribution is non-symmetric. So since chi-square is not symmetric, we'll need to look up two critical values. From a table. So that is going to be something a little bit different for us. We have to look up two values instead of just one. Now, the same approach applies. We use the chi-square distribution. We develop our confidence interval by solving for sigma squared, or solving for variance. So you set up your probability right here. It's your probability calculation, and then solve for variance to develop your confidence interval. So solve for variance in that inequality. And now we have our confidence interval. Basically, this is our lower bound, and this is our upper bound for our confidence interval. So a whatever percent confidence interval for the variance sigma squared of a normal population. Oh, that's important. Highlight that. That's a normal population. So we are looking at the variance of a normal population. So we need to know that somehow. We are looking for a confidence interval for the variance of a normal population. So this is only valid for normal distribution that we're trying to find the variance of. So this is the formula. Now the hardest part is finding these two critical values. So we have to find two different critical values here. So we need two critical values. And what we're going to do is look those up in the table. So I'll show you the table. Here it is. This is the chi-square table that at least that we're going to look at. So this tells us the critical values for a chi-square distribution. Let's say you wanted chi-square. Let me see. Let's say we wanted chi-square 0.99, comma 5. So that would be the chi-squared value for the degrees of freedom 5 that has 0.99 to the right, and that would be this value 0.554. So 0.554. And then we also might need the corresponding chi-squared 0.01 comma 5. So go over to 0.01, that's down here, 15.085, so 15.085. And that would be our two critical values that we would plug in to that formula for the confidence interval for variance. We are definitely going to have a review day on Friday. I'm going to do some of Chapter 8 today and then some more Chapter 8 Wednesday. And then we are definitely going to have a review day on Friday. Just going to work review problems. First, I'll answer questions if you guys have questions, of course. And then I'll work some problems I just randomly pick from the book, more or less. And yeah, the exam, don't forget, next Monday is our exam. So our exam's going to be next Monday. So good question, good question. Other questions so far, questions about the material, questions about the exam or the outlay or where we are. We're a little bit ahead, which is a good thing. I don't want us to get behind, that's for sure, especially with everything going on. So we're a little ahead. We're not supposed to start Chapter 8 until after the exam, so we're in a good spot. I definitely want to have plenty of time for the final exam, do a little review for that as well. So yeah, we're in a good spot overall. So we got another question here. What chapters will be covered on the second exam? The second exam will be chapters 4, 5, and 7. So 4 was all the continuous distribution stuff, 5 was all the multivariable distribution stuff, and then also the central limit theorem. And then chapter 7 has been confidence intervals for the mean, and now confidence intervals for the variance. of a normal population. So that is what is going to be on the second exam. Continuous distributions, joint distributions, continuous and discrete. Also, central limit theorem is in there. And then confidence intervals for the mean of a large and small sample size, and then also confidence intervals for variance. Also, don't forget, confidence intervals for population proportion is also going to be on the exam. So exam is only chapters 4, 5, and 7. That's right. That's right. And this is the end of chapter 7 for us. So these confidence intervals for variance is the very end of our chapter 7. So we're going to basically stop here for the exam material. Like, this is the last thing on the exam for next Monday. All right, cool, good questions. Make sure we're all on the same page. Don't ever want to have anybody left behind because of confusion. That's for sure. Cool. I don't know if anybody ever watches Bizaardvark. I know I certainly don't. That's definitely not why I'm making this reference. But if you were to have heard of that show before and watched it, there's a guy on there. Not that I watch it, but he definitely says "coo." So hopefully I didn't just like lose half of you because I referenced Bizaardvark. All right, just trying to spice it up a little bit, trying to mix it up, you know? Miss you guys, miss this little banter back and forth, and we don't do it as often as we should. Keeps life interesting, keeps the class fun and exciting. So, yeah, man, it's missing you guys. Hope you're all doing well. Hopefully you're safe. Hopefully you avoided the bad weather yesterday. That was some more bad stuff yesterday. No questions, we'll keep moving on. All right, let's go back to the confidence intervals over here. So that's our formula. This is how we get the confidence intervals right here. Bam. That interval of values. Now, let's look at an example. Let's say actually an example straight from our book. It says breakdown voltage of electrically stressed circuits. And we have some data in the book, and those values are like 1470, 1510, etc. And we have a sample of size 17. So we have 17 values, 17 circuits, and we figured out that the breakdown voltage in the circuits was the sample of 17, these values. So we want to know, what is a 95% confidence interval for the variance? So what is a 95% confidence? I think I dropped a few people there. We had 34 viewers and now we have 31. So, I lost some people with the Bizaardvark reference. Oh well. All right. So, what is a 95% confidence interval for the variance? Now, assuming this, of course, this assumes a normal distribution. Assuming normal distribution. Is underlying the breakdown voltage. So assuming that the breakdown voltage is normally distributed, what is a 95% confidence interval for the variance? So we can estimate, well, the sample variance, we can calculate that. My goodness, I hope you remember how to calculate sample variance. So how do you calculate that? Beats me, coach. Well, go look it up. It's at the beginning of the whole book. It was like one of those test statistics that we talked about, chapter 1. It's actually kind of up here. There's kind of it right there, except you divide by n-1, so that's why that's over here. It actually could be over here. But that's kind of it right there. So that's a sample variance. So, now, our degrees of freedom for this chi-square distribution is going to be the sample size minus 1. So n-1 is going to be 17 minus 1, which is 16. All right, so the thing we skipped over, unfortunately, is a normal probability plot. That normal probability plot indicates normality. So that means we can actually verify it's normal. But yeah, we're good to go. So now, what do we need to do? Let me go to the chart over here. And what are we looking for? We have a 95% confidence interval. So let me erase this stuff that we had earlier. We have a 95% confidence interval. What does that mean alpha is? Well, that means alpha is 0.05. So alpha is 0.05. All right, so let's see, 95% confidence interval. All right, that means alpha is 0.05. And we need alpha over 2 to the right and alpha over 2 to the left of our critical values. So we're going to look for chi-squared 0.025, comma 16, and chi-squared 0.975, comma 16. I'm actually writing those in the wrong place, but we need both of them. So let's see, 16, go down to that row. So here's my 16th row, and I'm looking for 0.975, which is right here, so 6.908. 6.908. That's going to go in the lower bound denominator, 6.908, and then go over to 0.025. There it is, 28.845. 28.845. So those are our two critical values that we need for our denominators. So let's go back and make sure that's what we got. So here is our critical value, chi-squared 0.025, comma 16, goes here, 28.845, that's what we got. Chi-squared 0.975, comma 16, and that goes, let's see. Yes, the 1 minus goes to the upper bound, and the alpha over 2 goes to the lower bound. So yeah, this one goes here. I was right. I don't know why I second guessed myself. There we go. So that's where those denominators go. And then you just do a little plug and chug. Here's your n minus 1. Here's your s squared. Here's your n minus 1. Here's your s squared. And then your critical values down here in the denominator. Plug and chug that in a calculator, you get about 76,000 up to 318,000. So that's a confidence interval, 95% confidence interval for the variance. So 95% confidence interval for the variance of the breakdown voltage of these electrically stressed circuits. And then you take the square root of that to get the confidence interval for the standard deviation. So this would be a 95% confidence interval for sigma. So it's somewhere between 276 and 564. So cool, man. That's pretty much it for the variance. It's just a different chart. The hardest, I mean, it's not really that hard, but the hardest part of this is just knowing that, okay, I have a new chart that I have to read, and where do I put the values? Well, just keep in mind this formula right here. So this formula right here is just your bread and butter for this confidence interval for variance. So you read the new chart, know where to put the values, and you get your confidence interval just like that. Questions? I'll pause for questions here. Try not to keep flying by. Just wait to see if anybody has any questions. We'll be back in a second. Yes, I'll attach a z-table, t-critical, and chi-square criticals to the exam. So pretty much this exact chart right here will be attached to the exam. So you'll need the chi-square chart, critical values, I'll attach that. You'll need the t critical chart, I'll attach that. And you'll need the normal distribution, cumulative distribution function, standard normal, I'll attach that. That's right. You just need to know how to read it correctly. Okay, that's your focus. I'll try not to give you more than 40 degrees of freedom. Otherwise, you have to use this stupid gross formula. Sorry, my kids would get on to me for saying stupid. You have to use this extremely inconvenient formula down here. Questions? Good question. That's a great question, actually. But if you have the book, they're in your book, so you can look them up there if you want. That way you don't have to print them out or keep scrolling through the PDF of the exam. Let's see, this one is A11 in the book, at least for the version I have. So, good stuff, good stuff. Good question. Anything else before we move on? All right, cool. Let's not get too ahead of ourselves, but let's at least start hypothesis testing for single samples today. It's not too bad. I think you'll catch on pretty quickly. And then next time we'll do some more chapter 8, significantly more, hopefully, maybe even finish chapter 8, we'll see. And then Friday we'll review for our exam coming up next Monday. So hypothesis testing. This is very similar in what you can do. You can use a confidence interval, or you can use hypothesis testing to test claims made by people using data. So basically people say, okay, my data shows this. And then you could say, okay, is that statistically significant? So the question we want to answer is someone's claim. So is someone's claim statistically significant? Statistically significant. Right? They're saying, okay, the average is 40. So I think that the average is 40 or greater. Is that claim statistically significant? Whereas maybe the manufacturer said that the average was supposed to be 30. So maybe they're saying, no, the average is actually 40 or greater based on this data that I've collected. You might say, okay, is that statistically significant, that claim that they're making the average is 40 or greater? This happens a lot whenever you're looking at filling bottles, like at a bottling company, let's say Coca-Cola or Pepsi or whatever. I used to have, we used to buy these little Kool-Aid drinks for our kids, and you could see inside the bottle, like the one that has a little top that you twist off and everybody puts it in their mouth pretending that it's a retainer, when you're like 6 or 7 years old. And you could see like in the bottle itself, you could see at the top, there was like a different height for the liquid in the bottle, like visibly. And you say, oh, wow, it's not exactly like 10 ounces or whatever it claims on the bottle. It's like either a little more or a little less than 10 ounces because not every bottle is exactly the same. Some were like really close to the top and then some were like really far down. You're like, whoa, wait, what's going on? Well, the average supposedly is 10 ounces. So I could take 6 of those bottles from the package that I purchased and I could say, okay, well, in my 6, the average was only 9.4 ounces. And then I could say, that means they ripped me off. And then somebody else would say, well, is it statistically significant, 9.4? Is that the amount that you're below? Is that statistically significant? Or is that within the range that they show on their, advertising or whatever's in the fine print? So that's kind of the that's kind of the idea. Today we're going to basically test whether or not claims made by people based on data are statistically significant, or if that deviation or that variance in your result can be explained with statistics or probability. So is it within the range of probable deviation, or is it outside of that range of probable deviation? So whenever you get outside of the range of probable deviation, then you can start to say, oh no, it's statistically significant because this should only happen less than 1% of the time, and it happened. So I think, bam. Yes, I know everyone lives the same childhood. That's exactly right. We all did that with the Kool-Aid little caps. I'm sure it's a choking hazard now. It wasn't a choking hazard when we were kids, but all right. So test procedures. What do? Somebody, you or somebody else, makes a claim about some parameter. Usually the mean, could be other statistics that are other parameters like the variance, or it could be population proportion or whatever. But you make a claim about some parameter value. So you make a claim about some parameter value. Or you can make a claim about several parameters, or you can make a claim about the shape of some distribution. These are all like claims that you could make, statistical hypotheses. All right, so these are examples down here. The first example, you can make a claim about the mean being exactly 120. Or you can make a claim about something called rho. I don't know what that could be. We'll see later. Rho could be less than 0.5. And or a difference of means. You have two populations. We'll talk about this in chapter 9. So this will be chapter 9. Two populations. The difference of means equals 0, meaning the means are the same, or the difference of means is greater than 5. So mu1 is greater than 5 plus mu2. So these are all statistical claims that people can make based on data. They say, oh, I think the mean is larger than some value. So now I want to know, is it statistically significant? Is the claim that they made statistically significant? Is it verifiable with, like, is it outside of the normal range of deviation from what the manufacturer claims or whoever made the initial claim? Now, the procedure is to first develop something called the null hypothesis. That's really just the claim that the manufacturer makes, or that, you know, somebody who defined the thing, they said, oh, it's this. So that's the null hypothesis. The alternative hypothesis is a claim that contradicts the null hypothesis. So a contradictory claim to the null hypothesis. So if the evidence from your sample suggests that H0 is false, the null is false, we reject H0. So if it's statistically significant, this data that we collected, so if the data produces statistically significant evidence, then we may reject the null hypothesis, the claim, the initial claim by the manufacturer, or whoever made the initial claim. We may reject that claim if we have enough evidence, statistically significant numbers. So the statistically significant result. So if the sample does not strongly contradict H0, i.e. it's not statistically significant, the data, the result that we have from our data is not statistically significant, then we cannot contradict H0. We fail to reject H0. So we really only have two outcomes here. We either reject the null or we fail to reject the null. Okay? So it's either wrong or we haven't proven it to be wrong yet. That's kind of the way science works, right? Like that's how science has always kind of worked. It was like, okay, I'm going to pose this, and until it's proven wrong, we will think that it's okay. So we'll fail to reject it. But once it's proven wrong, bam, it's gone. It's like F equals ma goes out the window as soon as, you know, quantum mechanics and general relativity kind of proved that these other things are true that F equals ma can't really explain. So F equals ma was not rejected until it was. So it's kind of the same thing here. We either reject the null or we don't reject it yet. So we never prove the null. So that's kind of important. That's right here. We never prove the null hypothesis is true. We just keep failing to reject it. That's kind of like a scientific approach, I guess. If you do reject the null, then you accept the alternative. If you fail to reject the null, then you kind of like reject the alternative, but you're not really proving the null. Anyway, it's kind of a hairy topic. So we need strong evidence to reject the null. What's strong? What's strong enough? So I don't know. Maybe our sample mean shouldn't go below 9 ounces, except 1 out of a million times. And we got a sample mean of 8.4 ounces. Well, that would be statistically significant. So, all right, the general format, typical cases, theta could be any population parameter. For us, most of the time, we're going to start off at least with the mean. So for us, we're going to look at the mean of a distribution. And our null is going to be that the mean is some particular value. So, or theta, any general parameter, is going to have a particular value. Don't worry about this terminology over here too much. Yeah, don't worry about that terminology. So the idea behind hypothesis testing, I'll just read this. It says, suppose that H0 is true and the population parameter is equal to some given value, theta sub 0. What is the probability that a random sample will give me a value, a sample estimate, theta hat, as large or small as the one that I got? So you say, okay, the manufacturer claims the average amount is 10 ounces. Well, I got 8.4 ounces in my bottles, all of them that I added together and got the average. Is it statistically significant that I got 8.4? What's the probability that I would get something 8.4 or below? If that's a really small value, if it's really unlikely to get that, then there's probably something wrong with the manufacturer's claim. That's kind of the idea behind hypothesis testing. Of course, the more data points you have, the stronger or the easier it is to get a statistically significant result, or know whether or not it's statistically significant, I guess you could say. So let's look at this. Test procedure based on data. 3 years ago, 20% of people used Windows XP. That's not true, is it? Hopefully not. See, 3 years ago, people were still using like Windows 10. So let's change this to Windows 10. Well, we'll say Windows 7. 3 years ago, well, yeah, that makes sense. 3 years ago, 20% of people still used Windows 7. Is it the same now? So probability, the proportion of people that used Windows 7 was 0.2, or 20% of all the people. The alternative is that we think it's actually less than 20% now. So is it 20% now? Or is it less than 20%? So less than 20% now. So we will ask 200 people at random. So this is our data collection. So data collection. Ask 200 people at random. X is going to be the number of people that use Windows 7 out of the 200. If the null is true, then X follows a binomial distribution. Sample size 200. Probability of success 0.2. We expect 40 people, because that's the expected value of a binomial, we expect 40 people to still use Windows 7. Would you reject the null if the sample, in the sample, if we had 39 people use Windows 7? Would you reject the null if it was 38? What about 30? What about only 1? Which one is strong enough? That's the idea. Which one is statistically significant? You say, okay, which one is strong enough? So how many people would you need to say that they still use Windows 7 to say, oh no, it's definitely not 0.2, it's definitely less than 0.2. So where is it enough to say the number or percent, the proportion of people using Windows 7 has gone down from 0.2. So that's the idea. That's the most important thing about hypothesis testing, is understanding what you're doing. What are you saying? Is it likely that the value has actually gone down? How do you know? What's statistically significant? How do you know if it's enough? Okay, that's the idea. All right, it's another example here. Let's see, body weight increases after entry into college. A common belief is that during the freshman year, students gain 15 pounds. We want to test this hypothesis, and we get a sample of 40 students. So we collect data from 40 students. We estimate the average weight gain, and it's 13.7 pounds, and the standard deviation is 2.93. So the sample standard deviation. If it is true that the weight gain is 15 pounds, then for any sample, the random variable would follow some distribution. But we have a sample which is large, so this is approximately normal. So this would be approximately the normal distribution, 0, 1, because we have a large sample. We do not have sigma, but it's fine, no worries, because the sample size is large. We can replace sigma with S. So we're basically invoking the central limit theorem right here. So basically by the central limit theorem, if you have a large sample, then this thing follows a normal distribution, a standard normal distribution. So the corresponding z value, if we plug in S instead of sigma right here, we get negative 2.80. Would come from a standard normal distribution. Our hypothesis is to test that the average weight gain in the population of all freshmen is 15 pounds. Our alternative will be that it's less than 15 based on our data. So this is kind of based on the data, but usually given in the directions of the problem. What is the probability of having a value of negative 2.80 or smaller? So what's the probability basically of x bar being 13.7 or smaller? So that's the same question. What's the probability x bar will be less than or equal to 13.7 if mu were equal to 15? That's the idea. So what's the probability that x bar would be 13.7 or smaller if mu were 15? The same question is asking what is the probability of having z less than or equal to negative 2.80? Okay, well, what's the probability that z is less than negative 2.80? Well, that's phi of negative 2.80, which is 0.0026. Probability very small. Most likely, mu is not 15, because out of our sample of 40 students, we got an average of 13.7. So we could reject the null because this probability is very, very small. So now I said 0.1, but it depends on the problems. Problem may tell you a different value to check. Is it smaller than 0.05, or is it smaller than 0.1, or is it smaller than 0.2? So it just depends. It just depends on the problem. So, any questions? Questions so far? Now, this thing that we calculated is called a test statistic. So for different tests, whether we're testing the mean or population proportion or whatever, we get a different thing called a test statistic each time. So this test statistic for population mean is always something that we calculate in this process. So we always calculate this in the solution process. There are other test statistics depending on the parameter we want to test for and the sample size and or conditions. So let's look at what could go wrong. So if we get a small probability, then we might say, okay, maybe the null is wrong, but it's actually right. So maybe we accept the alternative when the alternative is true. Well, that's good. This is a good thing. Maybe we accept the null when the null is true. That's also a good thing. Well, that's actually really just saying fail to reject the null when the null is true. Maybe we accept the null when we shouldn't have. So the evidence was not strong enough. Evidence was not strong enough. So we fail to reject the null. And then maybe we accept the alternative when the null was true. That's also bad. So evidence was strong, but it was the one time it could have happened. So these are types of errors. So these are two types of errors that might happen whenever we do these hypothesis tests. Type 1 error, let's see, type 1 error right here, is when we reject the null when it is true. All right, that's not good. We accept the alternative when the null is actually true. So that's, let's see, in the court of law, the null is that the defendant is innocent until proven guilty. Well, maybe we had evidence that was strong, but the defendant was actually innocent. So you had strong evidence against the defendant, but the defendant was actually innocent. Not rejecting the null is when someone who is guilty isn't prosecuted. So that's the type 2 error. You fail to reject the null, or you fail to reject that the defendant is innocent when in fact the person is actually guilty. All right, so we want these probabilities to be small, which means we want a small error rate. Cool. Let's stop there. We'll go into these errors a little bit more next time and go through the general hypothesis testing next time. But let's take a break. Kind of sprinting through everything. So let's slow down a little bit and take a break here. We'll come back on Wednesday, finish up chapter 8, or most of it at least, and see what's going on. Get ready for that exam next Monday. So, any questions before we head out? Make sure we take our time. Looks like we had one disgruntled viewer today. That's exciting. 7 thumbs ups. Also exciting. All feedback to me is good. I like all feedback. Not that the thumbs up or thumbs down are really feedbacks, but all feedback to me is good. Like, I like to rate my professor. I like to read your comments. I like all kinds of feedback because especially, unfortunately, bad or negative feedback helps me learn a lot more, but good feedback is, good too. Positive feedback is good. Helps me keep doing the stuff that I think is good. And then I figure out what's not working as well whenever I get those negative comments or negative feedback. So helps me improve either way. So I'm good either way. Let me know what's up. Make sure we're on the same page. And now we're blowing it up. That's what I like to see right there. Blowing it up. Now, I definitely don't want to keep doing something poorly if I am doing it poorly. So let me know if there's anything that I can do better, of course. So yes, I believe you're absolutely right. I'm sure it was somebody who joined a little late and then they were like, oh man, Bizarrebark, I just don't get it. So yeah, I definitely would have downvoted anything that referenced Bizarrebark. Just kidding. Bizarrebark is one of our favorite TV shows. So it used to be. We don't watch it anymore. It hasn't come on. It's kind of been cut off of TV. Most TV just kind of sucks nowadays anyway. So, oh well. So sweet. Thanks for stopping by today. Hope you guys had a good weekend. I'll catch you on Wednesday. If you have any questions, hang around. I'll be here for a little while. I'll answer any questions that you guys have. But yeah, thanks for joining us again today. Have a good one.